everyone, and welcome to our webinar today. Yeah, I'm very pleased that you took the time today to participate in our webinar. My name is Markus Eberle and I will moderate this webinar, but way more important is the man next to me, Dominik Köck, our expert today. Dominik, hi, nice to have you here.
Thank you.
So yeah, today's topic is about the basics of optoelectronics. And yeah, I'm excited. I think the last time I've heard about light and how opto is working was while my studies. So I know that I will learn some new things today. And yeah, I'm excited. I hope you are as well. And yeah, so the stage is yours, Dominik. Have fun.
Okay, thank you.
Thank you.
So yeah, thank you for the kind introduction. I'm Dominik. I'm in the company of Würth Electronics since now 5 years as a product manager in optoelectronics. Before that, I studied bachelor and master in basically semiconductor physics. Basically, I know the background of what kind of semiconductor structures you need to build to be able to get light out of semiconductors. So what you need for an LED. And then after my studies, I started here in Würth Electronic, mainly at the beginning a little bit with optocouplers, then ultraviolet LEDs, and now my main focus is optical sensors. But I will give you an introduction of the entire optoelectronic portfolio, and my goal is also to give you basic knowledge of the different terminologies of the LED technologies. So first I want to start by explaining you what is light, what are the different application areas, so you get a broader picture what this actually is. So most of you guys know visible LEDs is they emit light that we can see with our eyes. Visible LEDs means they emit light in the wavelength range of 400 nanometers to 750 nanometers. And this is, light is just electromagnetic radiation. So all electromagnetic radiation is characterized by some wavelength, and it just happens that you define the optical or the light as a certain wavelength range. And in this wavelength range, we have the visible light, 400 to 780. Then we have two lower wavelengths. We have the UV, which is from 100 nanometers to 400 nanometers. If we go to even smaller wavelengths, we go to X-rays and then gamma radiation. So it means if you go to lower wavelengths, the energy is higher. And on the other side, if you go to larger wavelengths, the energy is lower. So because of this, the different wavelength ranges are useful for different things. So of course, visible light, it's what we see with the eye. So visible light is really useful for anything to showing for signaling, is something on or not, or for illumination. So of course, white LEDs for illuminating a room. The UV, because it has a higher energy, you can use it for curing applications of some glues, or if you go to UVC at 270 nanometers, you can have such a high energy that you can use this light for disinfection. On the other hand, if you go to much larger wavelengths, you end up in the infrared region. There, every single photon has less energy, but the light is still invisible. So this kind of wavelength range, the infrared, is very useful to transmit data or sense objects. Because first, it's like lower energy, so it's not so dangerous for the eyes. And second, it's like invisible to the human eye, so no one gets annoyed when you have some optical sensor that is sensing something with infrared. So we have optoelectronic components in like all of these different wavelength spectrums. So here you see an overview from our website. The LEDs, IC LEDs and 7-segment displays, they are all for displaying something or like signaling something. They all emit in the visible range. Then we have the infrared components, optical sensors and lasers. They emit in the infrared range. Then we have ultraviolet LEDs, which of course emit in ultraviolet, UVA and UVC. And we have optocouplers. They are a little bit special. They don't emit the light. They have just an infrared LED inside and also an infrared detector on the other side inside the package. So I will get more into this later, how this is built up. But basically it's like an infrared LED and phototransistor inside one package, just that the light doesn't come out of the package. So first I want to give you a better understanding what is, how is a LED built up? So what's inside, what's important? So the key or the most important element in the LED is the chip. The chip is a semiconductor material that is where the light is really made. So if a current is flowing through the chip, so this is basically a semiconductor PN junction, then you get light with different wavelengths depending on the type of semiconductor material that you use. So at the top I mentioned a few typical materials: aluminium, indium, gallium nitride, and so on, and different materials, compositions you use for different wavelengths. So then the other thing that you need to operate an LED is not only the chip, but you also need to put current through the chip. So you need to connect it to the lead frame, which is then in the end soldered on the PCB. You need some substrate for strength and also heat conduction. And depending on the specific product, you also have some optics or lenses on top. So here is an overview of different LED types. First, I want to show you chip LEDs and PLCC LEDs. So to get you a better understanding, what are the different types of LEDs available? The chip LEDs, this is what you mainly use in basically all applications, just to show they are really small. They are use low power and are not very bright. So they are just used in applications to show is something on or off, just some indicator LEDs. On the other hand, the PLCC LED, they are a little bit brighter, but you can use them for similar applications, but where you want a little bit brighter signaling. And the reason they are brighter is because they have this kind of white housing that is really good in reflecting the light up. So you get more light out of the package. So here again, this one is a cross-section of an LED, of a chip LED. What you see, there's a chip in the middle. This is where the light is made. Then there's some wire. This is to connect it. And the chip is on some lead frame, which you can solder on the PCB. And it has some substrate. In this case, this is PCB substrate, or for the PLCC, this is some type of plastic. And you have some cover of the chip, some silicone or epoxy, which is protecting the chip itself from external influences. If you want to have a little bit higher power, so you want to put more current through the chip, or you want more light, then you end up, or you want to use ceramic or QFN EMC packages. So if you want a higher power, of course you need a larger chip. And with a larger chip, and if you use a higher current, then you get more electrical energy being dissipated as heat. This is why you have more thermal dissipation that you need to take care of. So because of this, it's good to make this large chip on a ceramic substrate. So this ceramic substrate has a really good thermal conduction. So it's really good in moving the heat away from the chip into the underlying PCB. Something similar you can do with this EMC packages. There you have the chip basically directly soldered on the lead frame, on the metal lead frame, and then you can also have a really good heat conduction out of the package. Here I want to show an overview again of the, or like a comparison of the different LED types. So what you see, I showed you the chip LED, PLCC, EMC and ceramic. And the difference here is the maximum power you can use and of course the different optical output. So the chip LEDs, you will use them, so they have a low electrical and optical power. And so when do you use this? For signaling something, if something is on or not. Some indicator LEDs. And I guess most of you guys will be using just chip LEDs because these LEDs are just everywhere in every application. If you want the LED to be a little bit brighter, you use the PLCC LEDs, which can have a higher optical output. And we have like PLCC and chip LED in all different colors, like single color, multicolor, in the visible range and also in the infrared. This, if you want to go to a like higher power, so when do you use a higher power? When do you want to use higher power LEDs? You want to use them when you try to illuminate something. So not when you just want to see the LED, but if you want to make the LED shine light on something so you can see this something. So for all illumination purposes, you would use like the higher power LEDs. So of course for the higher power, okay, you have higher electrical power and much higher optical output. So all of these different types come in standard sizes. So the chip LEDs, the standard sizes are, we have them in all typical standard sizes that are available on the market. Here it's important to know that the chip LEDs, the size is in units of inch, while for PLCC and the EMC ceramic, the sizes are always in millimeters. So it means that the 3535 is 3.5 millimeters by 3.5 millimeters. Okay. So now I want to go more into detail of like optoelectronic parameters, so you get a better, deeper understanding what we show in the datasheet. What are the differences between different types of LEDs? To get a better feeling of what we actually show there. So first I want to start with white LEDs. So there we have XY chromaticity coordinates and the color-related color temperature. So let me explain what this means. So there is something called a chromaticity diagram, which is just this kind of diagram where you have x-axis, y-axis, and then all the different colors plotted here. And you can use like xy coordinates now to specify exactly the position where you are on this map. So this is why, for example, in the datasheet for the white LEDs, we have this quality, the color coordinates as well. But we not only have this color coordinate, we also have the correlated color temperature. So color temperature goes typically from 2700 Kelvin for white for warm white LEDs and 6000 Kelvin for cold white or cold white LEDs. So it's like more bluish light, while the warm white is more like a reddish white. So where does this come from? How did anyone come up with the idea of a correlated color temperature? So there is an effect that any body that has a temperature emits electromagnetic radiation. And there's a law, depending on the temperature of your object, you have different amount of radiation. And this is shown here in the black body spectrum. So a body of 300 Kelvin, this is about the body temperature of a human. It emits mainly around, in the infrared region, around 10 micrometers. But if you heat up, so for example, if you use a metal, you heat it up so it glows, then it starts glowing somewhere here, it's something around 1000 Kelvin. So you see a little bit of reddish light back here. If you heat it up even more and more, then it goes more into orange, or if you heat it up much more, then it goes to yellowish, and even if you put it higher to higher and higher, temperature, then it goes more into the bluish range. So the reason, for example, we see the sun as something like yellow is because the surface of the sun is around 5,000 Kelvin. So this is the sun is basically a black body emitter, and we see a similar curve like this, this yellow curve here. Okay, so the idea of LEDs is now to make something similar to this correlated color temperature, but of course only to use wavelengths that are in the visible range. So if you have a black body spectrum like this, you see a lot of UV, a lot of infrared as well being emitted. For LED to be really efficient in electrical power consumption, you just want it to emit here somewhere in the visible range. And actually, because of this, we now have white LEDs that are much better than those old lamps used to be, which were based on the thread which was heated up to a high temperature. Okay, so this is for white LEDs, but of course we also have monocolor LEDs or single color LEDs. For the single color LEDs, you use typically the peak wavelength or the dominant wavelength. So the peak wavelength, if you look at the spectrum, so here down is the wavelength versus the intensity. Peak is of course where the maximum is, and the dominant wavelength is basically the color that is perceived by your eye. So for visible LEDs, what you most want to look out for is mainly the dominant wavelength. If this is similar for this, like for our product, then for example with a competitor product, then it looks the same for the eye. On the other hand, if you use infrared or UV LEDs, they don't have, don't emit in the visible range. There we use a different value called the centroid wavelength, which is basically the center of mass of the whole spectrum. But there most of the time the peak wavelength is the relevant one. Another concept for you to understand is the viewing angle. So what you will typically find in any LED datasheet is a graph like this, where you have the angle versus the intensity. And this viewing angle, it just gives you an idea of how much light is emitted to the top or versus to some certain angle. So maybe you've noticed, but most of the LEDs that exist have a viewing angle somewhere around 120 degrees. And there's a simple reason for this. So imagine the chip. We have some chip, this is some area. It emits light in any direction without any preference. But if you look from the top on the chip, you see a larger area than if you look from the side of the chip at a certain angle. And when you calculate all this out, what you will end up is exactly this kind of curve with a 120 degrees viewing angle. And this is then called a Lambertian source. But of course, many times you want to have a more focused emission. Then if you want to do this, you need to have some optics on top of the LED. So here you see, for example, a simulation with 100 degrees versus 30 degrees of viewing angle. So what you see is the light is much more focused. So here you have a much higher amount of light per area per surface area. And here on the right side, I'm also showing some simulation of what happens with the irradiance. So irradiance is basically the power per square meter that is coming to a surface. So I calculated this versus the viewing angle of an LED that is keeping the same optical power output. And what you see there is if you go to lower and lower viewing angles, you see the irradiance goes really up. And there you understand, if you go to really low viewing angles, you understand why lasers are dangerous. For laser pointers, for example, they have a really, really low viewing angle. So the amount of light per area is really going up a lot. So you have a high amount of light on a small area. This is why laser pointers, you shouldn't look into laser pointers. Okay, some other units that are necessary for quantifying the amount of light coming out from optoelectronic components are here the luminous flux and luminous intensity. So for your understanding, the luminous flux, there you use this mainly for LEDs that are meant for illumination. Why? The luminous flux is giving you basically the amount of light that is emitted by the LED in all directions. So it just takes all the light. If compared to this, the luminous intensity, it's not looking at all the light, but only that the light that is emitted to the front into a certain solid angle. So into a certain angle, only this light that comes to the front is being used for the luminous intensity detection or like quantification. So when do you use this? When do you use this value? When do you use this value? Most of the time, if you have an illumination application, you use the luminous flux because you want to know what total amount of light you get out. If you have a signal LED, you just want to show if something is on or not. You're mostly interested in what's coming to the front. So most of the time, the signal LED is just you want to see, okay, how much comes if I look into it to the front. This is why it's a industry standard that most of the time you'd use the luminous intensity for quantifying the brightness of the LEDs for the signal LEDs. Then there's some other properties, the illuminance and the luminance. So the luminance is, it's not an LED parameter. It is just what happens if you put a light source somewhere and you want to know how much light is hitting on a surface. So it is the amount of light per surface area. And the luminance is also not an LED datasheet parameter. So the luminance is if you have a whole big surface that is all of it is emitting light, then you use this. For example, for displays, you use something like this. But again, this is not so relevant for LEDs. So then for the different brightness quantities, so how bright an LED is, I showed you the luminous quantities. So those are called photometric quantities. This is the brightness that we see or perceive with our eyes. On the other hand, like the more scientific values would be the radiometric quantities. So the luminous flux would be the radiant flux. It's just given in the units of watts. And the same for the other properties. So now the relation between those two quantities is, so if we want to go from the radiometric quantities to the luminous or photometric quantities, we multiply the spectrum by the eye sensitivity curve. So it means this one is what we see with the eye. This one is basically what the like a detector or like the scientific detector would detect as a quantity, a light quantity. So this is really an energy. This is just what the eye sees. On the other hand, we can have some similar brightness quantities for horticulture lighting. So horticulture lighting means you can use LEDs, light for growing plants. And there, of course, it's interesting what kind of light does the plant like. And it just happens that there is a plant sensitivity curve as well. So there's a certain amount of light that is useful for a plant. And if you use this plant sensitivity curve, you get from the radiometric quantities, you can go to this horticulture brightness quantities. So another thing I want to show real quick is some efficacy of LEDs. So I just want to show you here some data. What happened, like here the first red LED was developed in the 1960s. And you see that the amount of light was increased over the decades a lot. So the efficiency or efficacy increased and increased over the light, and now we are like much like orders of magnitudes better than we used to be in the past years. Because of this rapid increase of the efficiency over time, we like nowadays you also have you basically use only LEDs, white LEDs for lighting purposes. You don't use the old old lamps anymore, so, you know, the tubes, or you don't use the ones with the filament inside anymore. On the other hand, another thing, a nice graph I want to show you is what happens with the efficiency when you change something with the temperature of the LED. So the light conversion inside of the chip is really the efficiency of this conversion process is really dependent on the temperature of the chip itself. So if you operate the LED at a really high temperature, then you lose a lot of efficiency. And you can see this also the similar effect if you just use the same LEDs and just increase the current a lot. Then of course you have a much higher current temperature inside of the package, and what you see is the efficiency goes down quite a lot. So what we learn from this is if you use LEDs in an application, it's always good to make sure to have a good heat dissipation away from the LED, and maybe don't drive them at like the overall maximum, because you will lose some efficiency, and if you drive them at the overall maximum, you will also reduce the lifetime of the LED. Another thing I want to mention real quickly is for basically all LEDs, we offer photobiological safety certificates, or like a test report showing how this is a report showing how dangerous an LED is. You know, almost all LEDs are not dangerous at all. You can just look at them and there's no problem. But if there's a really, really bright LED, especially in the blue region or in the ultraviolet region, this can be dangerous for the eye. So you know this, for example, if you look into a lamp, a really bright lamp, then you see the points everywhere. This is basically this blue light hazard. So this is the damage that you can have when you look into some blue light. For visible LEDs, most important is actually this, or most difficult, most dangerous is this blue light hazard. There are also other different photobiological hazard mechanisms like UV. Those are mainly like chemical processes happening. And on the other side, thermal, so infrared radiation and thermal. Those are basically just if you have so much light that it heats up your cornea, then this of course will be a problem. But for LEDs, typically those two are not a problem. Blue light is only a problem for mostly a problem for really bright, high power blue LEDs, and only for a few ultraviolet LEDs you need to be careful about this UV hazards as well. So if you have like any more questions, or you want to see some reports, you can just get in contact with us, then we can share this for all the LEDs. Okay, now I want to give a quick overview of different products in our portfolio. First, visible LEDs. So visible LEDs, we have them in all different possible mounting options. Top view, they emit light to the top. Side view, emit, they're soldered sideways, emit to the side. Reverse mount, emit to below if you have a hole inside of the PCB. We have these visible LEDs in all possible, like all the different types of packages, PLCC, chip LED, ceramic, even still THT, in all different sizes. The same for like B-color, so 2 types of colors, and full color, so RGB LEDs. So if you have any any application, just check out our website. You will find a lot of different visible LEDs in all types of different packages. Now one extension of the RGB LEDs especially are the so-called IC LEDs. The IC LEDs, they incorporate IC inside of the chip, inside of the LED package. So if you have like classical RGB LEDs, if you want to have some, like you have multiple LEDs and you want to have some nice color effect, then you need a lot of traces to go to every single color, to tell every single color what to do. So the solution with the IC LED is that you don't need to contact every single color anymore, but you can put all of these IC LEDs in series and use some digital signal to give every LED the command which brightness and which color it should show. So here you see a simple principle how you can connect the LEDs. You just need ground and VDD in parallel, and then you have some signal line that is going in series through all of the IC LEDs. And with this, of course, you can do a lot of different colors depending on your requirements. Here a little bit more on the working principle and data transmission method. So the idea is that the MCU gives out like a big train of 24-bit data, and the first LED takes the first 24 bits. The second LED so it gives the rest of the train further to the next LED. So the next LED will take the second 24 bits, and so on and so on. And this way, every single LED can be set to a desired color or brightness. For the IC LEDs, we have already like a few LEDs in our portfolio, different sizes in top view and also side view. And you can use this in many different applications. In the end, you can use this everywhere where you want to have a nice fancy color gimmick in your application. Here's another overview of our portfolio. I also want to show you that now we have on our website available the so-called feather winning display. Those are a lot of IC LEDs put next to each other, and there you can display different pictures, colors, or text, and test the IC LEDs out. Another big product group is the horticulture LED lighting. As I mentioned already, we can use light to grow plants, and for this we need only certain types of light or certain types of LEDs. So because the plants they absorb light, but they don't use all of the light. They use specific wavelengths for specific processes. So in the end, we have, when you look at horticulture lighting, most of it looks like this red or mixture from red LEDs and some blue LEDs, and maybe some kind of some certain type of white. And with this, you can make the lighting much more efficient, because you give the plant only this kind of color or wavelength that it really needs for doing something. So if you want to look more into the workings of horticulture lighting, you can check out also our application notes. They will be also linked in the video. So if you want to know more about this, just check this out. Because of the horticulture LEDs are used for illuminating plants, of course you need a little bit higher power. This is why we typically use this ceramic type of package for this. But we also have a few EMC type packages that have a little bit lower power. They are more cost effective, but you cannot put through so much power. Another group is the UV LEDs. There we have this in UVA and UVC. UVA means 365 nanometers to 400 nanometers, and UVC is at 275 nanometers. So the UVA, you can use it for horticulture, but also for, mainly it's used for curing applications. If you want to cure some glues, industrial glues or adhesives, then you use this. On the other hand, the UVC, you can use it for surface and water disinfection. So this was really a hype during COVID, that you can use light to disinfect something. You can use it to kill coronaviruses. But of course, for UVC, you need to be a little bit careful because it has such a high energy that it can kill viruses. Of course, it's also dangerous for the skin and for the eyes. So there I also have an application note about UV, or especially UVC LEDs. So if you want more information, check this out. Then I want to switch quick to the infrared components. Infrared components, we have the infrared LED emitters in all different packages and sizes with different viewing angles and intensities. And on the other hand, if you want to detect light, we have the photodiodes or the phototransistors. For the infrared components, of course, you always want to be careful that the emitting spectrum is similar to the absorbing spectrum. So here in the dashed line, you see, for example, the emission spectrum of infrared LED, and the other dashed line is the absorption spectrum of a photodetector, so photodiode or phototransistor. You see, okay, they coincide. So you have the maximum amount of sensitivity of the phototransistor or diode where the LED sits. And those single components you mainly use to transfer some data or to build your own little optical sensor with this. For infrared LEDs, we have infrared LEDs, but we also have like VCSEL that emit in the infrared range. So if you have an application where you have a big an illumination, you can either use like those ceramic type infrared LEDs, but you could also use a VCSEL, which gives a much more homogeneous irradiation, because the type of VCSEL we have, so this is some kind of laser, but it's not focused so much, the light, because it has a glass filter on top, which is spreading the light out. And because of this, we can have a really nice homogeneous irradiation on a like rectangular surface. On the other hand, if you would look at the infrared LED emission, this would be like more in the middle, in the center you have the most light, and then it goes less and less to the sides. Another application where you would use the VCSELs is if you want to have fast switching, for example in time of flight applications, you want to have really, really short pulses, then you can also use the VCSEL for this. Okay, infrared, you use this in all different types of application, light barriers, security, switches, different types of sensors. But I want to also show you that, okay, we can make this even more. We can go to more like, more optical sensors. So to give you an idea what I mean with optical sensors, you can detect light or detect something with light. So for example, for the light detection, we have already photodiodes and phototransistors. They just see the light that is being emitted somewhere, and they can just detect this. But what you can do, you can put infrared emitter and detector next to each other, and then build a sensor like this. If there's light, light is coming up, and if there's an object, it's being reflected, and then you see it. And now, so I've introduced some new products that have been released a couple of weeks ago. Those are like 2-in-1 packages, optical sensors, where you have the LED and the phototransistor together in one package. Because of this, of course, you can have much more space efficient usage, and it works also really nice. So you don't need to take care of any crosstalk between the LED and the phototransistor, because we have a barrier already built inside of the package. So the first products that I have here for the optical sensors, they are really useful only for small distances, like like a few millimeters range. You see here the graph of the collector current of the phototransistor depending on the distance. Because of this small distance where they are really useful, they have a limited places of applications. So you can use this in ATMs, ticketing machines. So you know if, for example, you put a card in the machine or not. You can use it to see if something is open or not. So use it as some kind of optical switch or interlock, or you can use it as some rotary encoder. If you want to go to higher distances, you need to be you need a little bit more intelligence in your system, and there we are also working on some products to give you also like higher ranges of centimeters or even meters range. But now I'm almost finished. So this is now the last big group of optoelectronic components, the optocouplers. The optocouplers are like also LED, infrared LED and phototransistor just in one package. And the idea is, okay, if here the LED is on, then the phototransistor also is on and leaves current through. And the idea is here, you don't have any light going out, so it's not like this optical sensor, it's just inside of the package. And the important thing is you don't have any electrical connection in between. So this kind of component is really useful if you want to have some insulation between two different circuits. So you need this basically everywhere, in every different power supplies and home appliances. Everywhere you have like different circuits which operate on different noise levels. For example, the LED would be, for example, on the microcontroller side, and the phototransistor on the other side, which is like a more dirty circuit, basically. But because of this, the main application is to offer some insulation, and because of this, we need to have some certain certification that we have for all of our optocouplers. So we have the VDE, UL, and CQC, mainly for German and US market. Mainly the VDE and UL is the relevant one, and we can have like insulations of these components up to like 5 kilovolts. So there are different types of optocouplers, phototransistor, Darlington and Triac, that are already released in our portfolio. Of course, there can be more in the future. The main difference is, most of the time you use the phototransistor type optocoupler. We have this in all the different standard series that are also common on the market, and different package sizes and different CTR bindings. So mostly you use this kind of things in like power supplies. The same Darlington optocoupler, it has like basically two transistors next to each other. So you get a much higher CTR ratio, a much higher amplification of the current. But we also have now relatively new the Triac optocoupler. Here the output is not a transistor, but it's a Triac. What is a Triac? It's a component that can conduct current in both directions. So this is really useful for AC applications, especially like AC motor drivers. So what you need, for example, in the control of a washing machine motor, for example. And what you can do with this component, if the LED is on, then so you turn the LED a little bit on and on and on, and at some certain trigger current, the Triac is getting conductive completely. So this is a little bit a contrast to the other, to the Darlington and phototransistor. There, if you increase the current a little bit, then also the output current increases a little bit. But for those triac optocoupler, the main difference is here, once you pass this trigger current, this output is completely on. As mentioned, you can have the optocouplers in many different applications in every power supply, regulation controls, circuits, industrial controls, AC motor drivers. You need this in almost like every electronic circuit. So if you want more information on the optocoupler, but also on any other products, please check out our website. You can find also application notes and webinars linked in on the product pages, but also on the link, like in the links below this video. And please also check out our Red Expert. This is our simulation tool where you can look at the different parameters of optoelectronic components, but also of course other electronic components we offer as Würth Elektronik, and also different simulation tools, like for example for horticulture LEDs we have a horticulator. There you can simulate what kind of different light mixture, so if you use different LEDs, what kind of end spectrum you will receive from this, so you can play around with different color mixing there. Okay, then that's it from my side. So now please feel free to post any questions, and
Okay, Dominic, thank you very much for your presentation. And so from my side, I've learned a lot of new things today. So at the moment you should be able to see the download of the presentation, and also afterwards, so in the next few days, we will share the link to the recording for those of you who had some technical issues. So the recording will also be online, and also the slides. So now we have some time for your questions, and there are some questions which came in already. If we can't answer all your questions today, we will answer them later on via email. Or Dominic will answer them. Okay, so first question I can see here is why are some output powers in candela and others in watts?
So let me go back. Back to this slide. So here is an overview of different amounts of, so those are like basically different ways of characterize the brightness of an LED. So you can have this radiometric quantities, or you can have the photometric quantities. Radiometric is really the optical power in watts. So this is really like an energy, while these photometric quantities are in lumen. So this is like the radiometric quantities, but like convoluted with the eye sensitivity curve to really see what we are seeing. So then the question is now, why sometimes we use this, why sometimes this? For infrared and UV, they are not visible. So UV is somewhere here, infrared is somewhere here. So those photometric quantities would be just 0. So this is why for infrared and UV we use the radiometric quantities. And for visible LEDs we typically use the photometric quantities. And there the question, okay, candela is specifically the intensity. So intensity is, as mentioned here, the intensity is the amount of light that is being emitted to the front, not the amount of light being emitted everywhere. So it's like very common to use this intensity, what amount of light is emitted to the front for signaling LEDs, but for illumination you typically want to use all the light that is being emitted also to the sides.
Okay, thank you very much for the answer. Then we got another question from our same attendee here today. why are not always both the photometric and radiometric values written?
Well, this is the same answer. So
Yeah.
it's mostly it's not useful for infrared and UV LEDs. It just doesn't make sense to put both values. For visible LEDs, sometimes you could maybe put the watts, the radiometric values as well. But this is also not very useful because it's common on the market to look at the photometric quantities. So if you just look at the radiometric, it's not very useful to compare, for example, data sheets.
Okay, thank you very much. Then next question here. Okay, there is another one. Are there any advance on robust, long-life optocoupler that withstand harsh environments?
No, well, this is a very general question. What do you define as a harsh environment? I think I would take this later to. We can do this via email. In the end, it's depending on what is the question of your, like what do you mean with harsh environment? In the end, this is like all is like enclosed package. It's really hard to break something in there. So it's always a question, how do you define harsh for this? So I think we need to take this later.
Okay. Yeah, so also there the hint, if you have also any questions afterwards, if there are some questions coming up, then just contact us. You can use the contact form on our website, or we also have a chat online where you quickly can contact us, and also our experts are there for you. So then next question about isolation capabilities of phototransistors. How can this work for 5 kilovolts in those small packages effectively if you think about pollution or humidity?
Well, the inside, there's no problem. So inside, there's an insulating material that can withstand a really, really high voltage. So you will never get it's impossible actually in the lab to get like an overvolt or like overvoltage in here, or like some arc inside of the package. What happens if you put too much current, too much voltage on this package from this side versus this side? So there's a maximum insulation voltage. It's always between LED side and phototransistor side. So between this side and this other side. So what happens if you put a really, really high voltage, like more than 6 kilovolts on this optocoupler? You just get an arc outside through the air. So then you get, for example, so if you have a high humidity in just in your lab or in the air, you can even have like an arc just going outside. So it will not break inside. It's like a lightning happening outside, and then so there's it's really hard to break this insulation. So I've never seen this happening.
Okay.
How to do this? And this is just because this insulation material in there is like really good. So you always have really good insulation in between.
Okay, thank you very much. So then, next question. What is the maximum distance of an object you can detect with light?
Okay, so here is, for the first products that I have here, they are just in LED and some phototransistor next to each other in the same package. What you see here is the curve. What is the collector current versus the distance of a certain type of object? And what you see is, okay, if you go to a larger, like here for this part, to up to 5 millimeters, then you're down to something like 10% of the maximum value. On the other hand, for this kind of component, it has a smaller viewing angle, so it can basically look further away. There you need to go, or you can detect up to 10 millimeters, or like at 10 millimeters distance, you have like only 10% of the maximum value. Of course, if you can go even higher, if you make sure that you don't get like any noise from ambient light, and if you are able to filter out the ambient light. So you can do this by modulation of the LED. If you modulate the LED and then take here only the signal that is being modulated, then you can filter out the ambient light. Then you can increase the distance. And there are also like some parts in development that have some intelligence, some IC inside of the package, and then you could even go to like tens of centimeters, or sometimes like for certain components up to a few meters even.
Okay, so then I would say also time-wise, last question for now. So yeah, question here, will you also do high-speed optocouplers?
So as mentioned, there are different optocoupler types. So here phototransistor, dielectric triac. A high-speed optocoupler is similar to those guys. It just has a different output, and the output is in such a way that like it can switch much faster. So the thing is, when you use phototransistor, a phototransistor is always quite slow. It has like switching times of something around 20 microseconds, so you're not able to have a really fast switching. So what you do for high speed, so there's like products like 1 Mbit or 10 Mbit, where there you use not a phototransistor, but you use a photodiode inside, which is much, much faster. And this is then connected to some kind of other transistor, which can then switch much faster. This kind of product is in development, but it still takes a few months to release this. But please let us know, or let your sales know if you have any requirements there, then we can look at this already.
Okay, so then we are already at the end of our webinar. Thank you very much for your attention, and I hope, and yeah, we hope, I think, you liked our webinar, and hopefully we will see us at our next webinar. So thank you very much. Also, Dominic, thank you.
Yeah.
It was a pleasure, and have a good day.
Thank you.